Hello, my name is Ali. I'm a second year PhD student in the Department of Computer Science at the University of Illinois Urbana-Champaign. In this video, I'm going to present our work, Lost in Translation, a study of bugs introduced by large language models while translating code. This work is a collaboration between IBM Research and the University of Illinois Urbana-Champaign. All right, let's get started. In the past few years, LLMs have been used a lot in code generation and understanding tasks, and we've seen the rise of models like Codex, Code T5, and much bigger models like GPT-4, Gemini, and Cloud 3. Today, GitHub Copilot has been activated by over 1 million developers, and they belong to like about 20,000 organizations. So far, it has generated about like 3 billion accepted lines of code, which is very impressive for a code large language model. Given the success of large language models in generative tasks, we wanted to see how it performs in code translation. But before diving deeper, we should need to first define what is code translation. Code translation is the process of converting source code from one programming language to another. For instance, if you have this Java code here on the left, which prints the numbers between 0 and 4, its translation to a Python equivalent is going to be like similar to the one which is shown here on the right. So some motivations on why we need code translation is application modernization, where the idea here is to like modernize applications which are like written in very old languages, like legacy applications from the 80s and 90s, into much like better languages like Java, which has more support and more use cases. Also, it's very important to like migrate the application architecture from like let's say monolithic to cloud native applications. So, application modernization is a very important problem in the industry. Moreover, code translation is challenging as it requires understanding both syntax and semantics. So, previously, we have some transpiler techniques like C to Rust CXGO, which uses some heuristic in order to do one-to-one mapping of, um, let's say, code constructs from one language to another. However, the problem is that they don't generalize well for all possible pairs of languages. So large language models, the good thing about them is that they generalize well and they tend to generate more natural code. So we were interested in seeing their potential in code translation. However, the problem with existing like learning-based techniques is that they use very small models, like smaller than 1 billion per meter, and they fail to achieve very high test accuracy. So in this work, we perform an empirical study of large language model-based code translation on multiple programming languages, benchmarks, also like real-life projects. We answer multiple research questions like effectiveness of LLMs in code translation. We also create a manual taxonomy of translation bugs introduced by LLMs. We also compare LLM-based techniques with non-LLM-based techniques in code translation, and we propose some techniques for like mitigating translation bugs. First of all, about the empirical like setup of this study is that we consider models smaller than like 20 billion parameters due to some compute constraints, and the models we chose at the time of the study are all of them are the state-of-the-art models. So for code LLMs, we considered CodeGen, CodeGX, and StarCoder, and for general purpose LLMs, we consider models like GPT-4, Llama 2, and the other two models like Aeroburst and Vicona. So more models have been added to our study after like acceptance of this work, and please check out our leaderboard for an up-to-date list of models. As for the subject PLs, we considered the TOB score, and we considered like programming languages like C, C++, Go, Java, and Python. So the first research question is about the effectiveness of large language models in code translation. In here, let's look at our crafted benchmarks that we considered in this work, and also like the real life project. So for the crafted benchmarks, we consider data sets like CodeNet, and we sample 200 code snippets. We also consider Avatar, which comes with more unit tests compared to CodeNet and complements that. We also have Eval Plus, which is also a very well known data set, and translate this to Java. And we also consider two real life projects like Common CLI and Click. Here's the result for the different data sets and the effectiveness of different LLMs. So as you can see, GPT-4 ranks top here with an average successful score of 47.3%. In the second spot is StarCoder with about 15%, and the third spot is CodeGen. So we also performed some study on unsuccessful translation. So GPT-4 had like 47% successfulness. What about the other 53%? So in here, as you can see, there could be multiple sources of incorrectness, like unsuccessfulness, like compile error, runtime error, or functional error. This pie chart shows the distribution of different kind of errors that's happening in GPT-4 results. So most of the time, as you can see, we're facing with compilation errors, which has to do with the syntax problems in the generated translations. So this problem is more severe in open source models. Like as you can see, like 3/4 of the star coder and also CodeGen are facing with compilation errors. Um, what else we do with this unsuccessful translation is that we use manual, like human labelers, in order to create a taxonomy of different translation bugs. And at the end of our study, which lasted 630 hours, we come up with 15 unique categories of translation bugs. Please refer to the paper for more details about the 15 unique categories. But in a higher level, these 15 unique categories can be um, abstracted into 4 different classes. And now let's look at one example for each class to know more about them. So the first class is like syntactic and semantic difference between like programming languages. So in here, as you can see, there's a problem of duplicating source syntax to target language. We have an original C++ code, which calls a routine arctangent 2L, and the incorrect Go code in here is just copy paste that without knowing that it's available in Go code. And so that routine call is not available, and that's why it results in an incorrect Go translation. The second class is dependency and logic bugs. In here, we have the problem of missing library imports and definitions. So as for the missing definition, we have original C++ code, which contains a definition for solve method. However, in the translated Go code, the problem here is that inside the main function, there's a call to the solve method, but to the solve function, but it's never implemented before in the translated code. Finally, we have the data-related bugs. In here, most of these bugs has to do with reading from standard in and writing to standard out. In here, we have a Java code, as you can see, which prints the character h and the output of y-1 in the same line without spaces between them. However, in the translated Python code, you can see that it will have an extra space between h and y-1, which is an incorrect translation. So the translation bugs that we saw in like crafted benchmarks are very different than the one that happens in real world projects. So in here, let's look at some examples of them. But first, we need to emphasize that we are the first ever work to translate and investigate real world projects in terms of code translation. So the real world applications, they're much more different than crafted benchmarks and have problems like method overloading, exception, and inheritance like relations between different classes. So in this example, as you can see, we have multiple overloaded methods, add option with different signatures in Java, which is absolutely fine. But we used the GPT-4, our best performing model, to translate it to Python. It just added some suffixes at the end, which is not the proper way for translating overloaded methods in Python. So moreover, going beyond creating a taxonomy, we also try to find an automated technique to mitigate some like translation bugs, which are mostly compilation errors. So let's look at our prompting strategy here. So we have a vanilla prompting and feedback prompting. Our prompting can be seen into 5 different sections like this. The first part is common between vanilla prompting and feedback prompting, where we are reminding the model what the task is and give it source code to it and ask to translate it to a target language. However, for the second part of our prompt, it's only specific to feedback prompts, where if something is wrong, if there was an incorrect translation by the model, we basically provide a stack trace error log to the model, and then try to give this as a feedback in order to enhance the model's performance and let it know what was wrong. In the third part, which is also specific to feedback, like prompting, we like provide some more objective and constraint to the model that it should satisfy in the new response. And to further enrich the quality of the prompt, we put a sample test input output from our dataset in order to help the model further. And the final part is just something common with the specific large language models we used in our study. And that part is like common between vanilla prompts and feedback prompts. So we perform like iterative translation bug mitigation. In here, we dynamically craft prompts based on every kind of unsuccessfulness, like runtime error, compile error, or test failure. And our strategy is to stop if the overall improvement is not over 5%. So this figure shows the overall improvement after doing feedback-based prompting for every like LLM that we considered. So in here we have GPT-4. The overall improvement is about 14%. However, for open source models like StarCode or CodeGen and Llama 2, the improvement in terms of score is not like as like significant compared to GPT-4, but still good enough, ranging between 2% and 4%. At the end, so our last research question here is comparing LLM based techniques with non LLM based techniques. So this table shows the performance of transpilers compared to LLMs in certain pairs like C to Rust, C to Go, and Java to C Sharp. In here, as you can see, except for the C to Rust pair, where the C to Rust transpiler outperforms GPT-4 95% versus 61%, all other transpiler techniques cannot outperform our best performing model, GPT-4. So in here, we can see that based on our analysis, both approaches provide like unique advantages and weaknesses for code translation, but we see that an ultimate solution can leverage both the large language models and transpiler techniques in order to perform better code translation. Here is an example of what could be wrong in one of the transpiler like translations. The code here written at the top is a C code, is a Rust code, which is like a translation from a source C code by GPT-4, which uses a lot of Rust specific code constructs in order to solve this problem. However, the code at the bottom is something like generated by the C to Rust transpiler, and it has some like certain problems. First of all, it uses compiler directives which can actually introduce dead code and cause race condition with mutex logs. It also uses foreign functions from C, like printf and scanf, without like determining the buffer size, which can actually lead to some memory leakage. And also, it takes advantage of unsafe blocks in order to like generate the code, which actually circumvents Rust safety checks, and it's actually like contradicting with the whole promise of Rust. So there was a blog post published by the White House, the Office of the United States, the Office of the President of the United States, about the like support for more memory safe programming languages about 2 months ago. And so it's very important to have programming languages and write software in more like safe manner. So just to wrap it up, in this work, we investigate the effectiveness of 7 large language models across 5 different data sets in code translation. We identify and open source 15 root causes of translation bugs as part of our artifacts. We evaluate 3 non-LLM based techniques on our benchmarks and compare their performance to LLM based techniques. And to improve the overall performance of large language models, we propose an iterative prompt crafting technique. As part of our future work, we plan to use neurosymbolic approaches in order to enable like repository level code translation. Our artifacts are available online with the all of the taxonomy of translation bugs as well, and we have received badges like artifacts available and artifacts like reusable as well. At the end, I would like to mention that please check and contribute to our leaderboard. You can scan this QR code in order to reach our leaderboard to look at a very updated version of the different kinds of models that we considered in our study. Thank you so much.